everyone. Can you hear me?
Yes, yeah.
Yeah, thank you. So myself, I'm Arokya Agustin, going to present my research article on the title of Load Capacity of Bump Rhesus Foil Journal Bearing. My co-authors are Dr. Shravankumar and Dr. TVVLN Rao. So we are from Department of Mechanical Engineering, SRM Institute of Technology, Chennai, India. So my presentation outline are the following things: introduction, objective, analysis, results, and discussions and conclusion. So in the introduction, the gas foil bearings are self-acting and well suited for high speed and high temperature turbo machinery applications. That is commonly called as high speed machineries. The performance of gas foil bearings relies on a coupling between a thin gas foam and support elastic structure. Extensive analytical and experimental studies over the past decades have resulted in significant improvement in load capacity and stability of airfoil bearings. So there are many there are many studies that had done already on these areas to find what is a static and dynamic behavior of the gas foil bearing. The purpose of this study is to investigate the load carrying capacity of foil channel bearing with a bump rhesus. So that is what our objective. And before that, I want to explain what is air bearing or gas bearing. So it is used in the principle of aerostatic or aerodynamic principle. That is air bearings that use a thin film of pressurized gas to provide a low friction load bearing interface between the surfaces. The two surfaces do not touch so that it will avoid the friction. So if there is no friction, no wear and no wear particles, and the lubricant handling system is also minimized. It is one of the major advantages, and using lubricants in the bearing is also one of the difficult complicated one. The leakage of lubricants will increase the friction between the shaft and rotor, shaft and bearing. So this airfoil bearing ensures the shaft and foil are separated by air's high pressure, which is generated by the rotation that pulls gas into the bearing. So this pressure is achieved by rotating the rotor at the high speed. So here this represents the rotor which is rotating at the speed of omega, and this is our bearing, airfoil bearing. So the high air pressure is generated between this rotor and this top foil, so that it is uniformly distributed on this bump and the recess of the bearing due to this top foil, so that we can get the stable rotation of the rotor and good dynamic and static performance also. So the objective of this study is to develop the analytical model for the recess extent and the depth of the top foil, and to analyze compressible modified Reynolds equation using short bearing approximation based on bump foil compliance coefficient and a recess configuration, and also to compare the results of load carrying capacity, that is of foil journal bearing with and without a recess. So that is what presented in this presentation. And for these analyses, the compressible Reynolds equation based on short bearing approximation is analyzed. The hydrodynamic non-dimensional pressure in a bump recess foil journal bearing is iteratively solved considering the change in film thickness due to deflection of compliant foil surface. The simplified compressible Reynolds equation under steady state conditions considering the short bearing approximation is expressed as follow. This one: R by L whole square dou by dou Z PHQ by 2 B by dou Z is equal to lambda into dou PH by dou theta. So in this one, so based on this figure, this figure shows the bump recess, the schematic of bump recess in a foil journal bearing. The non-dimensional film thickness for a bump recess foil bearing can be obtained by using this bump thickness, H is equal to 1 plus epsilon cos theta minus HB plus alpha P minus 1. So here epsilon is the eccentricity ratio and HB is bump height, and P is pressure, alpha is compliance coefficient. So by integrating this equation at the boundary conditions of P is equal to 1 at the Z value plus or minus 1 by 2, by integrating equation 1, we are getting the this equation P minus 1 is equal to 2 lambda into L by D whole square dou pH by dou theta into 1 by pH cube into Z square minus 1 by 4. So the non-dimensional pressure in equation 4 is integrated along axial Z direction. So by integrating along Z direction, we are getting this following equation in the simplified form. The solution of this equation to this non-dimensional pressure is obtained like this, and by simplifying the above equation, we are getting non-dimensional pressure P minus 1 is equal to 1 by 3 in lambda into L by D whole square like this. The non-dimensional pressure is further expressed P in terms of P. So here we can apply the value of L by D, epsilon, and theta and HB value. The HB equation is already shown. So by substituting the non-dimensional values of these parameters, we will get the load carrying capacity. We will plot the graph between load carrying capacity and a different extent. So the non-dimensional load components along the radial and the tangential directions are obtained by integration of the non-dimensional pressure. So this is W is non-dimensional load carrying capacity along the radial direction. This W is along the tangential direction. So in this equation we are substituting the values and we are getting the resultant non-dimensional load, and the resultant non-dimensional load is expressed as follows: W is equal to root of W epsilon square plus W phi square, and the results are obtained and plotted like this. So the non-dimensional load capacities of bump recess foil journal bearing obtained based on short bearing approximation. And this figure shows the non-dimensional load capacities of bump recess foil journal bearing with the varying extent of top foil theta t. So in x coordinate we are representing theta t, and y coordinate the load carrying capacity. So the non-dimensional load capacity increases. From the graph we can understand the non-dimensional load carrying load capacity increases with the increasing non-dimensional bump height on top foil from 0.1 to 0.4. So bump height is increased from 0.1 to 0.4. For these two values for bump height, the graph is plotted to know whether the load carrier capacity is increasing or not. So in the extent when the theta t value is increasing along x coordinate, and the W is also increasing for the value of 0.4 rather than 0.1. So when the bump height is increased, the radial thickness between the rotor and the top foil is getting decreased, so that it is increasing the load carrying capacity of the foil bearing. So the non-dimensional load capacity increases considerably with the increasing top foil bump extent from 40 degree to 160 degree with the eccentricity ratio from 0.1 to 0.5. So for the for the eccentricity ratio 0.1, 0.3, 0.5. So for the bump height of 0.4, so we are getting the increased load capacity values for the non-dimensional load capacity for the value for the L by D ratio 1, compliance coefficient to 1, and a lambda bearing number is equal to 1. So when we are changing this L by D is equal to 0.5, we are almost getting the same results for the same set of parameters. And next, the non-dimensional load capacity, that is graph is plotted between the load capacity and the compliance number. When the compliance number is increasing, compliance coefficient is increasing, the load capacity is decreasing. So for all the value of bump height and eccentricity ratio, it's keep on decreasing and approaching almost to 0. So here also for the value of L by D 0.5, theta T 120 degree, and lambda bearing number is 1. For this also it is almost reaching 0. So from this we can conclude for the non-dimensional load capacities of bump recess foil journal bearing with the varying bump foil compliance coefficient for different L by D and eccentricity ratios, the non-dimensional load capacity increases considerably with the increasing non-dimensional top foil bearing. The non-dimensional load capacity decreases substantially with increasing bump foil compliance coefficient from 0.01 to 10. There is no significant improvement in the non-dimensional load capacity with increasing non-dimensional bump height on the top foil from 0.1 to 0.4 at a higher bump foil compliance coefficient. So from this, we can conclude the following things. The load capacity increases with both height and the extent of the top foil bump. The height and extent of the bump on top foil has significant influence on load capacity at lower bump foil compliance coefficient. The bump recess region on top foil has potential to enhance the foil bearing load capacity operating at a lower bump foil compliance coefficient. And these are the references we had taken. And thank you very much for listening and your patience. If you have any questions, now you can ask. Thank you.
Do we have any questions on the chat? Any representatives of the paper here?
Pardon? Hello?
Yeah. Do we have any questions on the chat, Dr. Leon?
Any?
Yes, I have seen one question.
Yes, sir.
Were extreme journal positions considered in determining the load capacity?
Okay. Audio is not clear. Hello?
Yes, you hear me?
Yeah, hear me.
Yes.
Yeah, I can hear.
Were extreme journal positions considered in determining the load capacity?
We have taken for 190 degree of rotation.
Yeah, and one another question.
Or 360 degree, 190 degree only.
How significant is the effect of ambient air temperature on the model?
I don't get you, sir.
Question was, how significant is the effect of ambient air temperature on the model?
So when the rotor is rotating, it is pulling the air from the environment. So due to the high rotation of the rotor, it is generating the pressure, high pressure between the rotor and the top foil. So this pressure acting as the medium between the rotor and the top foil. So it is bringing the stable condition between the rotor and the bearing.
And Dr. Thompson, do we have time for one more question?
Yes, go ahead.
Yeah.
Can the model be adapted to deal with different recess configurations?
Yes, sir. Yes, we can use this for different configuration. That's what this is my preliminary study. I have started my work in this area. So in the preliminary study, we have tried it for a different bump height. So in future, we are also going to try it for different configurations, surface configurations.
All right, thank you very much for your response. Dr. Thompson,
Yeah.
That's it then? No more
Thank
questions?
you very much to the presenter for both the presentation and the answers to the questions.